So we're going to go over the answers for the part 1 sample question on the practice exam that we did. So 1A, we want to write a balanced ionic equation for the reaction between lead solid and Cl2 aqueous. Okay, so that tells us that our two reactants are lead solid, PbS, and Cl2 aqueous. So I'm starting with that. My products, I'm going to look at the information that they give us up top. So it says that when Cl2 aqueous flows through lead solid pipes, some of the lead solid oxidize to lose 2 electrons. That means the lead would become Pb2+ aqueous. Plus, we get aqueous chloride ions forms. So what ion does chlorine form? It's going to be Cl-. It's going to be aqueous still. So since we're doing net ionic equation here, we're seeing what changes. The lead definitely changes from solid to aqueous. The chlorine also changes, and it's kind of slight because here we have Cl2 molecule, and it's going to an ion. So we are going to keep everything here into the net ionic equation. But what I do have to do is balance this. So I have 1 lead on each side, but here I have 2 chlorines and 1 chlorine, so I'm going to add a coefficient of 2. So everything here is going to stay in the net ionic equation. You could also do like an oxidation reduction and sum those two together to figure out what the net ionic equation is, because that's basically what's happening. Lead is going from 0 to +2. Cl2 is going from 0 to -1. Part B, we want to write the KSP expression for the dissolution of lead 2 phosphate. So looking at that bottom equation that involves lead 2 phosphate, remember KSP does not include solids or liquids. So my expression is going to be the concentration of Pb2+, coefficient of 3, that means I'm going to cube it, times the concentration of phosphate. And that has a coefficient of 2, so I'm going to square it. So this is my KSP expression for that second equation. Next, we want to calculate the molar solubility of lead 2 phosphate. Molar solubility is in terms of 1 mole of a formula unit of that salt. So we can plug in F to represent the molar solubility. For lead, we get 3 moles of lead for every 1 mole of salt that we dissolve. So that would be 3S cubed. And then for phosphate, we end up with 2 moles of phosphate for every 1 mole of salt. So that would be 2S squared. My KSP value for this equation is 1.08 times 10 to the negative 53. And that's going to be equal to 3 cubed is 27 S cubed times 4S squared. 27 times 4 is 108, and S cubed times S squared is going to be S to the 5th. And that's going to be equal to my KSP of 1.08 times 10 to the negative 53. Now if I solve for S, I'm going to divide by 108 and then find the 5th root of it. So I get a KSP value, an S value, molar solubility, of 1 times 10 to the negative 11 molar. Okay, so I can dissolve 1 times 10 to the negative 1 moles in 1 liter of solution. So this is our molar solubility for this salt. Part D, using the KSP values above, explain why the addition of PO4 is more effective at reducing lead ions in drinking water than Cl aqueous ions is. So there's 2 ways you can explain this. You could say that based on the 2 KSP values, lead 2 phosphate is already less soluble because it has a lower KSP value than lead 2 chloride. Adding PO4 to drinking water will shift the equilibrium towards the left, reducing Pb2+ according to Le Chatelier's principle. And since it is less soluble, it would be more effective than adding Cl-. You could also look at the balanced chemical equations in terms of molar ratios. So for every 2 moles of chlorine that we add, we would basically remove 1 mole of lead ions from the system, according to Le Chatelier's principle. For every 2 moles of phosphate ion that we add, we remove 3 moles of lead from the system, according to Le Chatelier's principle in that balanced chemical equation. So you could explain it either based on the KSP expressions, how lead 2 phosphate is less soluble, or you could also mention the molar ratios between the ions. Then we have part E. We want to solve for a Q value given the concentrations of lead and phosphate ions that they provide. And we want to know if the concentration of lead ions would increase, decrease, or remain the same based on this value. Okay, so for Q, remember our Q expression is going to be the same as the KSP expression, just at a different point in the equation. So I still have the concentration of lead ions cubed times the concentration of phosphate ions squared. They give me a concentration of lead of 1 times 10 to the negative 9 molar. And I have to remember to cube that. And a concentration of phosphate of 3 times 10 to the negative 5. And I have to remember to square that. When we solve for this, plug it into the calculator, you get a Q value of 9 times 10 to negative 37, which is pretty small. But if you look at the KSP value, it's 1.808 times 10 to the negative 53. So that means our Q is larger than our KSP. So we have gone past equilibrium. When Q is greater than K, the reverse reaction is going to be favored until the KSP equals Q, or Q equals KSP. So because Q is larger than KSP, the concentration of Pb2 plus ions will decrease because they are a product. So with the reverse reaction being favored, concentration should decrease. Equilibrium favors the reverse reaction in which solid lead 2 phosphate will precipitate until equilibrium is achieved. Part F says that it is found that there's more lead ions in hot water than those in pipes carrying cold water. Is this consistent with the negative enthalpy of dissolution? Justify your answer with Le Chatelier's principle. So first, I'm going to say, okay, a negative delta H value means it's an exothermic reaction. So heat is kind of like a product. So if we have hot water, that means we're kind of adding heat to the system, so we're adding product to the system. So that's actually that stress would actually shift equilibrium to the left, where we have less concentration of lead ions. So I'm going to say no. Negative delta H means the dissociation of lead ions is exothermic, so heat is released. If a negative delta H would be true, cold water would increase Pb2+, because the cold water would lead to heat being removed from the system, causing equilibrium to shift to the right in favor of the products. Okay, so I said it that way, but you could also talk about the other way, where if it was true and you add heat, then it would shift it to the right. So either way that you justify it is fine, as long as you justify it correctly. That was not a good explanation. But you could also talk about how adding heat would shift it this way. I just said if it was cold water, we would remove heat, which would shift it this way, which is what they're saying hot water is doing. So it would not be true. Okay. Let's see. Part G. A student claims that the bond angles are 90 degrees. Do you agree or disagree with the student's claim? Justify your answer in terms of VSEPR theory. We're going to disagree with the student's claim. Some of you disagreed and you had the right reasoning, but you mentioned the wrong geometry. So it might be good to have your VSEPR packet out that we did in class. That's like a quick reference to double check your names and bond angles. Since it is an open note test, that is not considered cheating. Only thing considered cheating is talking to a teacher or another student. So you can use your notes. Do not feel like you're cheating that way. But of course, referencing notes does take time. Anyhow, so we are going to disagree with this student. There are 4 bonding regions in that diagram. There are no lone pairs, so this would correlate with a tetrahedral geometry where bond angles are 109.5 degrees and repulsions of valence electrons are maximized. So 90 degrees would not be consistent with that. 90 degrees is consistent with an octahedral geometry, and that is not octahedral with only 4 bonding regions. Part H, they basically find that the student, there's an average bond, have a bond length of 162.5 picometers, which is consistent with this diagram. So this kind of has to do with resonant structures. So remember with a diagram like one, it's not that there is 1 double bond and 3 single bonds, although that's what we see in the Lewis structure. In reality, all 4 bonds are going to be the same length, but they're going to be an average of 1 double bond plus 3 single bonds divided by 4. So I find that average bond length for diagram 1. So I take, based on the information they give me, I have 3 single bonds, so that'd be 3 times 163, plus 1 double bond would be 150 picometers, divided by 4. I have an average bond length of 159.75 picometers. For the second one, where I have all 4 single bonds, my average is going to be 4 times 163 divided by 4, which equals 163 picometers. So neither of these is equal to 162.5 picometers, but this one is pretty dang close. This is a lot further off, so because this is a closer value, I'm going to say that that finding supports diagram 2, in which there are all single bonds in PO4. Okay, part I. Student generates the following particulate diagram. They use dashed lines to show hydrogen bonding and omits a lone pair of electrons for clarity. Identify letter corresponding to an incorrect hydrogen bonding interaction and indicate how the diagram should be changed to be correct. Okay. So remember, hydrogen bonding occurs between a hydrogen and an oxygen of different molecules. So D occurs between oxygen and hydrogen, B occurs between oxygen and hydrogen, C occurs between oxygen and hydrogen, but A occurs between hydrogen and phosphorus. So that is what I'm going to go with. A is incorrect. You could redraw it a couple ways. So if you think about it, H is slightly positive. O based on electronegative, or P rather, based on electronegativity would also be slightly positive. So there would be no attraction between those guys. So if I draw my phosphate, and the incorrect water was somewhere over here, there's a few things I could do. I could attach the H to one of these O's with a dash line, or I could do this O here.